All right, so our first test was yesterday. I can tell you I'm still grading. I have graded the first two problems. I have to grade the third problem. Still, hopefully, if all goes well, I'll get the third problem graded this afternoon. So, if all goes well tomorrow, we should have results of the first test. A couple of little kind of general things I wanted to mention. Especially going forward in our coming tests. One is that's the best way to say this. What came up for a few people, and for most people, this wasn't an issue, but like on the second problem of the test yesterday, uh, most of those there was no work to show, and so consequently, some of you uh, just put the answer in Canvas and did not write it down on what you emailed me. Going forward in the future, uh, what I'm going to grade is what you scan and email me. I am not going to grade that and go in looking in Canvas. Now, for a few of you, I actually did that on this test you had yesterday. I actually went in Canvas and looked and see what values you submitted. But I will not do that going forward. So anything, whether there's work to be done, if it's just writing down the answer, write the answer down on what you send me. Because in the future, I am not going to grade anything other than what you email me. Okay. Uh, Another thing that obviously didn't come up with most people yesterday, but when you email me your test, I will send you an email back letting you know I got it. Now, if it gets close to the deadline, say for yesterday, as it got close to 12 o'clock, I started getting a bunch of emails that coming in at the same time. So it's not going to be an immediate response because when I get you email me the test, I open it up, look at it, make sure it's scanned well, and I can read it, and then I'll reply and tell you I got it. So if it's close to the deadline, it may be 10 or 15 minutes before I get to yours to respond. But you should get an email back from me shortly after you submit it. If you don't get an email sometime, within 15, 20 minutes, surely after you submit it, then you need to contact me and find out, did your email not go through? Did I not get it? Or I can check, did I get it? I just hadn't got to it yet or whatever. But double check and make sure that I got your test if you email me. Don't take it for granted that the email went through. Okay. Now, with those are the kind of two general things I want to mention concerning tests going forward. But before we get started today, uh, I only had one slight technical issue there at the beginning that I know of, but now's a chance if anybody has any questions or comments or anything you want to comment on or ask me about as far as the procedure goes of what we did yesterday, because that's going to be the exact same procedure for all the other three tests that are coming. So if you had any suggestions, comments, questions, whatever about the testing procedure, now would be a good time to bring that up and let me know. All right, so I'm taking silence and nobody has typed anything. So I'm assuming then everybody was comfortable with the process and the procedure, which is good. Because again, that's the way it's going to be for the upcoming test. All right, so now let's get back into mechanics and materials. So I reckon this would have been Friday of last week before the test. Uh, in section 4.2, we were revisiting axial or deformation in axially loaded members, and we came up with this formula. Delta is PL over AE. Right, that would be the axial or the longitudinal deformation in an axially loaded bar. P is the axial load. L is the original undeformed length. A is cross-sectional area of that member, and E is the modulus of elasticity. Again, that's dependent upon the material. Now, if you've got a member that's got multiple loads or different cross-sections or different materials, we saw we would have to get the deformation of each segment or section and add those together. So to get the total, we would sum those up for each section. And we went through and we worked an example. Well, when we did where we did that. So that's basically where we stopped. We're going to work one more example, a little bit different type of example, but still making use of this deformation formula, PL over AE. Any questions related to this before we work another problem? Okay, so this problem we're going to work today is actually a problem I got out of your textbook. This is problem 425 in your textbook, and I'll draw the picture in a minute. But if you have your textbook there with you handy, you could open up and find what the picture looks like now if you want to. But we're going to try to find the displacement at three different points, C, B, and E. And we're also given some additional information. We're told that the rods B, E, and CF are a 1/4 inch diameter, A36 steel. All right, so we'll come back to that information in a minute. Let me take a second and draw the picture. Looks like we've got four members there. They're all pinned together. We've got this vertical member, got a pin support at the top. And then we got this horizontal member. It's got a pin support at the right end. We've got another short member pinned to that that's vertical. And then that's pinned to another horizontal member. I can't draw straight lines today. And we got another pin support here. So let me label these and put some dimensions. This is AB. This is CD. This is joint E, and this is F. All right, so this is 2 feet. CF is 2 feet long. This is 8 feet from C to E, and then 2 feet from E to D. E is 1.5 foot long. And this bottom horizontal member, we've got a 5 kip force right in the center. This is 6 feet long. This is 6 feet long. So let me make sure I got everything labeled. I got all the dimensions, I think. We're also told that these two horizontal members, DC and AB, are rigid. AB and CD are rigid. So these two members, the two horizontal members, we're assuming are rigid. Again, the purpose for that is in reality, those members would bend. And again, we haven't covered bending yet, so we're going to assume that they are rigid and don't bend. So these two horizontal members do not deform. So any kind of deformation or movement we're going to have is due to the two vertical members, CF and BE, deforming. Those are not considered rigid. Also, just an observation here, looking at our structure, those two rigid members, CF and BE, are two force members. So CF and BE are two force members. They're pinned at each end and have no loads applied in between those pins. So I know the force is going to be acting, in this case, since they're straight, the same direction as those members. So the force is going to be vertical in CF, and the force in EB is going to be vertical. All right, one other thing. We are not given the modulus of elasticity, but we are told what the material is. So this is a case where we are going to have to go to that table that's in the back of your book and get the value for the modulus of elasticity of A36 steel. Obviously, we're going to need that if we're going to apply this formula PL over AE. We need E. Now, I've got this is the table that we were looking at in the back of your book. Obviously, these are English units, so we want to use the table for English units, and we're looking for A36 steel here. And we come over here for E, the modulus of elasticity is 29 times 10 to the third KSI. So 29 times 10 to the third KSI. Again, that's the value we got out of that table. So if you're not given the modulus of elasticity, reference that table in the back of your book to get what the modulus of elasticity is. All right. So now I think that's everything we need before we start doing any calculations. So coming back to our problem, as I said a minute ago, any movement has got to be due to CF either stretching or compressing, or in BE either stretching or compressing. Those are only two members that can deform. So we need to know what is the force in member CF, what is the force in member BE. So let's just start by looking at this bottom member, AB. If we look at the free body diagram of AB, we've got support reactions here at point A. We got a 5 kip force applied here right in the middle. It's 6 feet, 6 feet. BE being a 2 force member, I know that force, I'll call it force BE, it's going same direction as a straight line that goes between E and B, which in this case is vertical, so it goes up. Could go straight down, but looking at my picture, I can tell you it's going to go up. But you could assume either way you want to. The sign will tell you if it's right. So all we need to do is just sum the moments about A. Choose a positive direction. And we can find what the force is in BE. So it looks like we're going to have force BE times it's 12 feet from A. causing a counterclockwise moment. That'd be a positive moment. 5 kips is causing a clockwise moment, so minus 5 times 6, and it's got to be equal to 0. And force BE, 30 divided by 12, looks like 2.5 kips. It's positive, I assume correctly. It's in tension. All right. So that's the force in member BE, 2,500 pounds, and it's in tension. It's going to get stretched. Let's go ahead and find the force in CF while we're at it, and then we'll come back and talk about displacements, because we're going to need to know what the force in CF is also. So let's draw a free body diagram of the horizontal member up here. This is DC. I'm going to call this force CF. That's the force in member CF. Here at E, right, this is where EB is attached, and we just found the force in that member is 2.5 kips. It's in tension, so it's going to pull down 2.5 kips there at point E. This is 2 feet, this is 8 feet. We got support reactions here, dy and dx. And what we're after, and what we need to know is what is that force? Remember CF, sum the moments about D, set that equal to 0. And we can find the force in CF. So CF would be causing a clockwise moment, so minus force CF times 10, this distance from D. The 2.5 kips causing a positive moment, and it's 2 feet away. So 5 divided by 10 looks like force CF is 0.5, 1/2. It's in tension. So CF is being stretched as well. So at this point, we've done our statics, and we found what the force was in each of those 2 force members. Pause a second. Any questions how we got our forces? All right, so with that, then let's see if we can figure out, because what we're asked to find is the displacement at these 3 points. Right? How far does point C here move? How far does point E move? And then finally B down here. Right? That's what we're asked to compute, is what's the displacement of those 3 points. So let's start by looking at this top horizontal member, CD again. Remember, it is rigid. D is a pin support that's attached to the wall. Point D doesn't move. Right? The only thing that's going to happen, if you look at this horizontal member CD, is it is going to rotate about that pin support at D. Right? It's going to, since CF is in tension, it's being stretched. Point C moves down, and that horizontal member CD is going to rotate about that pin at D. Here's D. Remember, it's rigid, so it stays straight. It does not deform. So what's going to happen, C is going to move down. It's going to move down from where it's located before the load is applied. And we've encountered this already. We're assuming for very small angles, very small deformation, we're basically neglecting the curvature. Right? In reality, yeah, this thing is going to swing around, a circular arc. But if we only go like this far, essentially that is going to be straight. Right? So again, it's not the first time we've used it. So we're assuming small deformation, which essentially means we're going to assume that this moves straight down and we neglect that curvature. All right, so what we're after, what we need to know is, what is that distance? How far does C move down? Well, C's going to move down however much member CF deforms. Right? It's going to be the deformation of member CF, which is PL over AE for that straight member. So however far CF stretches, that's how far C is going to move down. Well, we know what the force is now. We know P. We know L. We're given the diameter, so we can calculate the area. And we looked up E in the table. So let's just plug in our numbers. P was 0.5 kips. Now, be careful with units. Make sure everything's compatible. So if we leave this in kips, that's fine as long as, looking ahead, E here is in KSI. So as long as we're kips and KSI, we're okay. If one was, say, kips and the other was PSI, then we'd have a problem. We'd need to convert the kips into pounds. But units-wise, we can leave that in kips. Also looking ahead, it's in KSI. That's per square inch. So again, we want all of our length in inches or all in feet. I'm going to go with inches since everything else is going to be in inches. So that length, which is 2 feet, I'm going to multiply by 12 to get me inches here. Right, so just for purposes of making sure we keep our units compatible, just reminding you that's in kips, that's in inches now. A, it's a 0.25 inch diameter. So to get the diameter or the area of a circle, it's pi over 4 d squared, so 0.25 inches squared. Yeah, this is in inches, this is in inches squared. So we're good there. And then finally, E is 29 times 10 to the third, and this is KSI. So we're good with our kips and our kips per square inch, and everything else is in terms of inches. So our units should be compatible, and our answer will come out in inches. And I got 0.00843 inches. Right, that's how far point C is going to move down. Again, this definitely reinforces our assumption that we're talking about small deformation. I don't know if you were looking at this with the naked eye, you might see it move, but you'd be hard pressed to measure that unless you had some really high-tech, sophisticated equipment. You definitely couldn't measure that, by eyeballing it and then look and having a yardstick or a tape measure. So we're definitely talking about small deformations. Now, if this had come out to be like 84 inches, then that's pretty much useless information because that would definitely violate our assumption that we're using small deformation. All right, any question how we got the displacement of point C? Yeah, we're just getting how much CF stretched. All right. Now, to do point E, we can actually get that just from geometry. It doesn't require any mechanics of materials here. Still going on the same assumption. Right? The E is going to move straight down. We're neglecting the curvature. And we want to know that this is how far E moves. Well, we can get that a bunch of different ways just from the geometry. If it's me, I would probably just use similar triangles. I know this is 8 feet from C to E, and this is 2 feet. So we could just do similar triangles. And I know delta E is to 2, as delta C is to 10. Again, ratio of this side to that side got to equal the same ratio this side to that side. So delta E, how much E moves, it's just going to be 2 times delta C, which we just calculated, which was 0.00843 divided by 10. And we're going to get 0.0016. I don't know. I'll carry out 6. You could round that a little bit if you want to. It's fine. But that's how far E is going to move down, just from the geometry. Assuming, again, CD is rigid, it doesn't deform, change shape. All right. Any questions or related to how we got the displacement of point E? It's going to go down. Again, both of these we're going down. All right, well then let's turn our attention to B. And if we look at that bottom horizontal member AB, again, it's going to move down. We're pulling down on this thing. We're assuming it's really small displacement, and so we're going to assume that it moves straight down. And if I can draw a straight line here, right, AB is rigid, so it stays straight. And so we want to find this distance. How far does point B move down? Well, here we got to be a little bit careful because B is going to move down for 2 reasons. One, it's going to move down simply because point E moves down. Right when this horizontal member up here rotates down, right, point E moves down, that's going to move EB down. And so it's going to go down however much E moves down. Plus, it's also going to move down due to how much EB stretches. We found the force in BE up here, it was 2.5 kips. And BE is not rigid, it's going to be stretched. So it's going to move down also however much BE stretches. So we're going to take the displacement of E and add the PL over AE for section BE. Let's remember BE. All right, so everybody with me conceptually here, why B is going to move down, not only how much BE stretches, but also the top of BE is moving down this amount already. So we add those together, and that's how far B moves down. So let's put our numbers in here. So this is 0.001686. And PL over AE, our force, 2.5 kips. Again, just like up here, if we leave that in kips, we're okay as long as E's in KSI. The length of BE is 1.5 feet. So 1.5, we're going to multiply that by 12 again to get inches for the length. A, it's the rods BE and CF have the same diameter, so the area is the same as before. Pi over 4 times d squared. Again, that's in inches. And then E was 29 times 10 to the third KSI. And I think that looks like we got everything correct. And so add those up and 0.033 inches. Again, confirming we're talking about really small displacements here. So a bit different than the one we worked to Friday was the bar, had different forces and different cross sections, different materials, I think, but it's a good example. Again, you got to know some statics, figure out what the forces are. You got to be able to do a little bit of geometry, and you got to know axial deformation is PL over AE.
Mr. Walters,
Yes, sir.
why don't E and B move the same distance?
Because B is moving the same amount E moves, plus BE is going to stretch. Right, so if you're looking at point E here, up here, all right, so it's going to move down because DE rotates. But then you got, if this is member BE, it's being pulled in tension, so it's going to stretch. So this end is going to move more than that end. The top is just going to move however much E moves down. But this bottom part is also going to move down due to that member being in tension and stretching and getting longer. Does that make sense?
Yeah, I got it. Thank you.
All right, other questions about that one, this one? All right. So again, this was what's in section 4.2. It's applying the PL over AE to axially loaded members. The next topic we're going to talk about is let's see. All right, there we go. Is you're going to find in sections 4.4 and 4.5 in your textbook. We're going to talk about what we call statically indeterminate. Let's spell this. Terminate axially loaded members. So a new term that we haven't encountered in this class yet is what we call statically indeterminate. Basically, what that means, if it's statically indeterminate, means it cannot be determined by statics alone. So it can't be determined by using only statics. And by that, I'm referring to our equilibrium equations. There are three of them. Sum of forces in the x equals 0. Sum of forces in the y equal to 0. Sum of the moments about a point equals 0. So that's what it means. If you've got a structure that's statically indeterminate, means you can't solve it. You can't find all the support reactions or the force in any, cables or bars that are supporting this thing using just those three equilibrium equations. Now, an illustrative example, again, that's all, we're not going through and solving this yet, but just to sort of illustrate the point. Let's say we have this bar, and we got a pin support here at A, and maybe we got a cable attached to this. We'll call this B. And let's apply some force F. So we're pulled down on it. Now, you've solved problems like this before. This is what we call statically determinate. You can solve this using just statics. You got support reactions here, At A, you got pin support, two unknown support reactions. You're going to have some force in this cable, we'll call it FB. Three unknowns. Three equations, three unknowns. You can solve that. But what if we add another cable? What if, in addition to that cable, we come out here and attach another cable? We'll call this point C. Well, now, right, there's going to be some force in that cable as well. Well, now how many unknowns do we have? 4. Right, so we got 4 unknowns. There's only 3 equations. So unless you invent some new form of math, you cannot solve a system of 4 unknowns and 3 equations. You gotta have the same number of equations as you have unknowns to be able to solve that mathematically. Now, I'll caution you, one of the most common things I see students do wrong when they encounter a problem like this is, well, they'll sum the forces in the x direction, set that equal to 0, you get AX. Sum the forces in the y equal to 0, right? You're going to have 3 unknowns. Sum the moments about A, you're going to have 2 unknowns. So what a lot of students do at that point is, well, they need another equation, so they go sum the moments about a different point. That does not work, right? If you sum the moments about another point, you are not going to get an independent equation. You're going to get a multiple of one of the 3 equations you already have. You don't get a new equation by summing the moment about a different point. But I see students repeatedly do this, even though I try to enforce that and tell you, don't do that, it doesn't work. I see students do it all the time. Now, a lot of times what they'll do, they do something wrong, and so they actually get an equation that gives them an answer. The answer is wrong. If you do the math right, you'll wind up with something like 0 equals 0, or 10 equals 10, or something like that. That's useless information. So make sure, remember this, summing the moments about, say, a second point does not give you an independent equation. You got 3 equations to work with, and that's it. If you have more than 3 unknowns, you can't solve it using statics. So that's one way you get a statically indeterminate problem, is you have more than 3 unknowns. You could add some more supports in there and wind up with 5 or 6 unknowns. You'll never get there with those 3 equilibrium equations. Now, another sort of different way of getting a statically indeterminate situation is not having more than 3 unknowns. It's just the way it's configured. You may not have more than 3 unknowns, but those 3 equations just aren't sufficient to solve it. So another, again, sort of illustrative example here is, say we got this bar that's fixed at each end, and let's apply some force F here in the middle. Well, we're going to have some horizontal reaction force. Technically, if it's fixed, you would also have a vertical reaction force and a moment, but if we neglect the weight and assume this is the only force applied, those would be 0 anyway. But just taking those into account, you can't solve this using statics. You don't know what AX and BX are. Yeah, you could sum the forces in the X equals 0. Actually, we only got 2 unknowns here. Right? So 2 unknowns. Right? We don't know AX, we don't know BX. Well, if you sum the forces in the X, what you did is ax plus bx plus f equals 0. Right? You got that equation. That's good. But your other two equilibrium equations tell you nothing. Sum of forces in the y equal to 0. There are no forces in the y. Sum of the moments about, pick whatever points you want to set equal to 0. They're all collinear. All these forces act along the same line. Those, no help at all. So we got 3 equations and 2 unknowns, but the 3 equations we have are not sufficient to solve that. It's so statically indeterminate. So it's just kind of 2 illustrative examples of how we could get there or arrive at a statically indeterminate problem. But have no fear, we can still solve this. Right? So this is actually going to be learning something new that you didn't see these types of problems in statics. Everything you solve in statics was statically determinate. You could solve it. Well, solving this type problem it requires both statics, right? And by that I'm talking about our equilibrium equations. Right? So we're still going to have to use these equilibrium equations, but we got to have something else. That's not sufficient by itself. So solving it requires statics and what we know or have learned so far in mechanics of materials. And by that, I'm talking about deformation. And this is what he refers to. You'll see this terminology in the book. He calls compatibility. I can spell this right. Compatibility equations. So it takes a combination, both statics in our equilibrium equations and what we know about deformation. If you go back to this first example, right, we got 3 equations. If we had another equation, we could solve that. Well, where we get that 4th equation is by what we know about deformation. Right? Remember delta, we're going to be using that same formula, PL over AE. So if I can get a relationship between the deformation in these 2 cables, that's where I get my 4th equation from. And so that's kind of general theme. All these problems are going to use applying your equilibrium equations, taking what we just learned about deformation and getting some relationship between the deformation, and that's where we get the extra equation that we need. And now we're able to solve it. And what time we got? I don't want to try to rush through a particular problem. And we only got about 5-6 minutes left, so I think maybe that's a good place to stop today, and that's where we'll pick up tomorrow at 11, is we're going to take this idea and see if we can apply it and solve a problem like this that I talked about up there, or solve a problem like this, where it really does not involve using anything new. All we're doing is combining 2 things you already know. How to apply equilibrium equations you learn in statics, and how to calculate the deformation, which we just learned in mechanics of materials. We're just going to combine those 2 things. So there's nothing new in this section, right? No new formulas to worry about or apply. It's just applying what you already know to problems like you haven't solved before, right? Any question at this point about the concept of statically indeterminate. All right. Any questions about anything at this point before we wrap up today's session? Nothing? All right, so I reckon then tomorrow, again, what we'll spend most of tomorrow doing is we're going to solve a couple of statically indeterminate problems. And then we'll see, we may have time tomorrow to also start talking a little bit about, I think, temperature, effective temperature change, I think, is coming next. That's where we're at, and that's where we're headed. Same as always. If you have questions about something you want to hang around after I stop recording, we can talk about whatever you want to. But if I'm not getting any comments or telling me not to stop recording, we're going to wrap up this session now then.